All right, this is lesson 8 in our unit on differentiation. We sort of turned a corner with the chain rule. Chain rule is the big link between the past and the future for us. And we've spent a couple of days looking at implicit differentiation, which was good in its own right. On today's show, we look at related rates problems. Problems where one quantity is changing and that causes another quantity to change, hence the idea of related rates. So we're going to look at how rates interplay, and our strategy each time is going to be the same. We're going to run through a predictable strategy every time. We're going to have some figure, we're going to draw it, we're going to label it. Then we're going to figure out what we know and what we don't know. As former Secretary of Defense Rumsfeld used to say, there are known knowns and there are known unknowns. So you've got to know what you know and what you don't know. You've got to find an equation that relates the knowns to the unknowns. We differentiate both sides with respect to time, and then we evaluate at the appropriate point. So let's see if I can put this in a practice. Oil is spilled from a ruptured tanker, and it spreads in a circular pattern whose radius increases at 2 feet per second. How fast is the area of the spill increasing when the radius is 60 feet? So I want to draw and label a figure. For us, that means here's your oil. It's some circular disk. It has a radius. That radius is changing, so we use a variable name. Second, identify your knowns and your unknowns. When we say that the radius is increasing at 2 feet per second, we mean that the derivative of the radius with respect to time is 2. That's what we know. That's the only thing we know. Identify your unknowns. So what are my unknowns? What do we need? We need how fast the area of the spill is increasing. The area of the spill is changing with respect to time. We want dA dt when R is 60. Because dA dt will be different over time. So we need what dA dt is when R is 60. That's what we're looking for. So find an equation that relates the knowns and the unknowns. Is there an equation that relates the radius of a circle to the area of the circle? I say yes. The area of a circle is pi r squared. And once we do that, we're practically home free. Because step 4 says differentiate with respect to time. So I'm going to take the derivative on both sides of our equation with respect to time. The derivative of area with respect to time is dA dt. That's great. That's the guy we knew. That's the guy we knew that we needed. So that's fantastic. The derivative of pi r squared, that's a tougher go. Pi is a constant. R is a variable. So the derivative of pi r squared is 2 pi r to the first. And then chain rule demands that because we're differentiating with respect to time and R is not time, we have to multiply by the derivative of R with respect to time. Have to. It's a must. So then the last step says evaluate at the appropriate point. Well, at the appropriate point, I want dA dt. 2 is 2, pi is pi, r is 60, that's the appropriate point, and dr dt is 2. So what does that mean for us? That means that dA dt is 240 pi, and our units will be square feet per second. We use the same kinds of units that were given to us in the problem. As a side note, what if instead of R being 60, what if R was 80? What would that mean over here? That would mean that dAdt would be bigger, significantly bigger. And why does that make sense? Well, that makes sense because to keep the radius increasing at a constant speed, you have to be pumping in much, much more oil as the slick gets bigger. As the slick gets bigger, you need more area coming in to keep the radius increasing at a linear speed. Okay. 2. A spherical bubble of gum is filled with air at the rate of 2 cubic centimeters per second. Find dRdt when R is 3 centimeters. Going to go back to our process. Our process says, draw and label a figure, identify knowns and unknowns. Here's our figure. It is a spherical bubble. It has a radius of R. What are our knowns and our unknowns? We know that we're filling the bubble with air at that rate. That is an increase in volume. We are given what dV dt is. And we can sort of tell that because we've got cubic centimeters up there. And so cubic centimeters is a dead giveaway for volume. So what do we need? Well, we need dr dt when R is 3. It is kind of blatant. And by that we mean we want the rate at which the radius is increasing when the radius is 3 centimeters. The rate at which the radius is increasing with respect to time when the radius is 3 centimeters. So what now? I'm supposed to find an equation that relates the knowns and the unknowns, differentiate, evaluate. Well, do we have an equation that relates volume of a sphere to its radius? Sure we do. We know that the volume of a sphere is 4/3 pi r cubed. We know that from our geometry course. If it were to pop up on an AP exam, your teacher would give that to you. The College Board would give that to you. They do not assume that you remember how to find the volume of a sphere. So now we differentiate both sides with respect to time. The derivative of volume with respect to time is dV dt. The derivative on the right side, the 3 comes down, multiplies by the 4/3. Pi is pi. Power decreases by 1. And then we're looking to multiply by dr dt because we're differentiating with respect to time, not with respect to r. So the chain rule says we have to multiply by dr dt. And then everybody gets plugged in. dV dt is 2, r is 3, and we're looking for dr dt. So what is dr dt? It happens to be 1/18 pi. And the units on that, I should give room for the units on that. The units on that will be centimeters per second. 1/18 pi centimeters per second. And just as a quick thing to think about, what if R was 4? Then this would have been 16. dr dt would have been significantly smaller. Why does that make sense? Because if I'm pumping in air at a constant speed, then what happens to the bubble? Initially, it gets very big very fast, but as the bubble gets bigger and bigger, the way it gets bigger slows down as there's more volume. So one rate affects another, and that's why these are called related rates problems. All right, one more in this time, and this will be the kind of thing we're going to come back to for a couple of days. So I just wanted to hit a couple of standard questions in this time with you. Jimmy is running from second to third base on a standard baseball diamond. So here's Jimmy. Jimmy's just trying to get to third base. He's here, and he's going this way. It's a square with a side length of 90 feet. Jimmy's speed is 30 feet per second. At what rate is his distance from home plate changing when he's 20 feet from third base? There are a couple things in play here. Here's Jimmy's distance to home plate. Let's call that D for distance. The other thing that's changing is Jimmy's distance to third base. We'll call that X just for fun. So what we have is a right triangle where X is getting smaller and D is getting smaller, but we're interested in D. So our knowns. Jimmy's speed is 30 feet per second, which means that, by the way, that's very fast. Dx dt is negative 30. Because X is getting smaller at the rate of 30 feet per second. X is getting smaller at 30 feet per second. So then what do I want? We need the rate at which his distance from home plate is changing when he's 20 feet from third base. That's what we need. So I need an equation that relates X and D, and in this case, it's X squared plus 90 squared is D squared. It's the standard Pythagorean theorem. And we're going to take both sides, we're going to differentiate both sides with respect to time. So the derivative of X squared, that's 2X, times the derivative of X with respect to T. 8100 has no derivative. Well, it has a derivative at 0. And so the derivative of d squared is 2d dt. And so we have a nice equation that relates x and d and their derivatives. So we just shove everybody in. When x is 20, dx dt is negative 30. When x is 20, d is the square root of 90 squared plus 20 squared. 90 squared plus 20 squared, and that's 8,500. And so d dt is negative 600 over the square root of 8,500 feet per second. Again, it's negative. Why is it negative? Because as Jimmy gets closer and closer to third base, Jimmy's distance from home plate is getting smaller. It's not getting smaller as fast as his distance from third is. That's about negative 6 feet per second, as opposed to the negative 30 feet per second that we had going to third base. But still, his distance from home plate is getting smaller, so we would expect a negative answer. Okay, that gives you enough of a head start to be able to come into a lesson knowing a little something, and then in the next couple of video lessons, we'll look at some classic problems, how it's going to pop up on an AP exam, all that good stuff. All right, thanks everybody. See you tomorrow.